Hello, everyone. Uh, this time we continue with our discussion about coplanar waveguide resonators. So that, well, in particular, let me share the iPad. So essentially, what we want to do here is we will continue discussing the lecture notes that I provided. So, in the previous lectures, we were essentially discussing about the Lagrangian for this system we have here. So essentially, we have this is a coplanar waveguide resonator, which is essentially the central part of the transmission line. And for this model, we basically, this is a very old problem, which is quite similar to the one when you have mechanical oscillators coupled together in a 1D array, essentially. So here we have LC resonators, and the coupling appears because we have this inductance here, essentially. So here, indeed, we obtain the transmission line Lagrangian, which is this part. Okay, this is something that we already discussed in the previous lectures, and something that is interesting here is that if you compute the motion equations using the Euler-Lagrange equations, which is this one, okay, in general. But one important point here is that we should obtain the Kirchhoff laws at this point. So at point 1 here, at the point n, at this node, okay. But also you should obtain the motion equations or Kirchhoff laws for a generic node here at the bulk of this resonator. Okay, so if you do that, for instance, the case for at the very, let's say, at the beginning of the resonator, so at essentially this coordinate is 0, which means taking in the discrete part, taking the Euler-Lagrange equations for the flux node 1, phi 1. So then here you can really prove that there is an equation, okay, which will be a boundary equations later on when solving the Sturm-Liouville problem that we will face here. Okay, so this is an important point. This is one equation that will give us some boundary conditions at the beginning of the transmission line. Then at the end of the coplanar waveguide resonator, we have this equation. So essentially, again, you look for the Kirchhoff laws or motion equations for the last node in our transmission line. So then we obtain this equation, which is there is a difference. If you compare this equation with this one, there appear a minus signs here in front. Okay, but this is nothing but you see there here there appear this flux node is in a larger position as compared with this one. Okay, but then well, here's the same, but in front of this in the discrete version there appear a minus sign that appears here in the continuum when we go to the continuum limits. So those are the two equations for the boundary conditions. Then, as I mentioned previously, at the bulk, so if you write down the Kirchhoff laws for a generic node, let's say node J, for instance, or whatever, I mean, you choose the notation you want, and basically what we obtain is the wave equation. And here there is a characteristic propagation velocity, which is this one. So it's 1 over square root of LC. And these quantities here, probably I didn't mention previously, but, or maybe yes, well, anyway, this L is the inductance per unit length of the resonator. And this quantity, small c, is capacitance per unit length. Okay. So this is the characteristic velocity, propagation velocity here. So we have the essentially the wave equation. So here we start the new discussion that, of course, as you probably know, this is a linear equation. Okay. And in order to obtain some solution for this wave equation, we propose a typical ansatz, which is we separate variables. So we assume that this, which is essentially, this is a classical field, which is a flux, and we separate variables. So this function will be a function that depends only on time, and there is a function that depends only on the coordinate c. Okay. And this is quite standard. So you replace this ansatz here into the wave equation. And of course, you should be able to prove that there appear two equations, one for the spatial part only, and for the time-dependent part. Fortunately for us, those are very common ordinary differential equations, which is basically represent a kind of a harmonic oscillator. Okay, and with these two solutions here that appears in 1 and 2, we should be able to solve the problem. Okay, notice that I mean, of course, when you apply this ansatz here, there should appear a constant term, which should be larger than 0, so that you may define the allowed frequencies in our system in this way, in terms of this constants here and the velocity of propagation. So of course, here we have well, you may also write, instead of 1 of LC, you may put B squared. Okay. Okay. And then instead of this term, you may write in this way, so that it is clear that this constant K should be some wave vector. Okay. So let me go back this way. And all the things that we need to solve here is to find what are the allowed frequencies in our system. Okay, so we have a wave equation with some boundary conditions, and then as you will see, this is nothing but a Sturm-Liouville problem for some differential operator, which is second order in this case. Have a look. This is something that, let me explain a bit on this. So we have, this is our answer. And of course, if you replace back into the wave equation, we obtain those two solutions, 1 and 2, but also you can plug this solution into this boundary condition and this one. Okay, this is the next part of the procedure here. So whenever you do that, so again, here using the ansatz, you may prove that there appear two additional equations, okay? Something that relates the function un, the ansatz, at c equal to 0 with the derivative of the function evaluated at the same point. So essentially, this is the boundary equation at the very beginning, of the transmission line. And then equation 4 is nothing but when you replace the ansatz here. You can really prove this, okay? It's just a little bit of algebra here. Okay, so I expect you try to, you should be able to reproduce those two equations, 3 and 4, but also, of course, 1 and 2, okay? So here's the main discussion here today is the following. So we may ask, what is the normalization conditions for this solution? I mean, of course, if you have this equation, you should be able to already propose a solution for that equation, of course, in terms of find a linear combination of cosine and sine, of course. Okay, but before proceeding with that case, let me discuss a bit on what is the problem we are facing at this point, which is essentially, as I mentioned, a Sturm-Liouville problem. So if you pick this equation 1, and you may write in this way, so you pass this second derivative to the right part, sorry, okay? But then you are left with an equation in this way. So you have you see here, this is a differential operator acting on a function, and then you have some value here and the function. And as I mentioned here, this is nothing but an eigenvalue problem for this differential operator, which is a second order differential operator. Okay. So you may see like this, no? If you want, what we have here essentially is an operator acting on a function, and then we have some eigenvalue here, lambda n, un. Okay. So this is first of all an eigenvalue problem. Something that is interesting here is that you may prove that this operator, this second order operator, differential operator, is self-adjoint. What is the meaning of that? So suppose we take the inner product of a function u and a new function that result from the action of this self-adjoint operator acting on some function defined on the same Hilbert space we have here. So our definition for this, so imagine we have two functions, u and b. So we define our inner product in this way. So an integral between 0 and L, the variable, which is the integration variable set, and then we have u square, sorry, u star, which is the complex conjugate, b of z. So this is essentially the definition we are using for the inner product, essentially. And then we use this definition for this part. So we have, you see here, we have the integral dz, and then we have u star. But then this function is nothing but the application of the differential operator acting on b. But remember that by definition, this differential operator has a minus sign here. So this is why appears this minus sign here in front of the integral. And the way to proceed here is quite easy. So we may integrate by parts. So this part you may write in terms of you can really prove that this is essentially this equation, where you may simplify. So one of these d set, which is a square, simplifies with this one, and then we are left with a differential of the first derivative of the function b. So here we integrate by parts. So this part is integration by parts. Then we have minus function u star, the first derivative evaluated between 0 and L. And then we have the integral of the derivative of b and the differential of u star. Okay, and then what happens here is the following. So we have we already integrate by parts. Sorry. So then you see here that this part of the integral here, you may pass this differential here, and then you again integrate by parts, so that you may be able to show that they appear now this product here. So we have the differential, the first derivative of u star times b, evaluated between 0 and L. And you see those terms are evaluated between 0 and L, so they are called boundary terms, okay? But also you are left with this integral where they appear the second derivative of u star. So this is interesting because what we see here is that we have boundary terms plus you pass this minus here, and then everything is star here. So essentially, what we have here is boundary terms plus a term which is essentially in terms of a typical situation of Sturley problems, this term you may write in this way. So this is L dagger u times inner product with b, essentially this one, okay? But what we can see here is that this L dagger is nothing but the same operator we have. So L dagger is essentially this one, and this is L, the same operator. So it's not changed. There is no any change here of the second order operator. So this is the definition. So whenever L dagger equals to L, but have a look, when we work with continuous functions, this is the way to compute L dagger. So you need really to see what is the action of L. So from here, you should be able to recognize which is the operator L dagger, which is in this case is L, okay? This is not always the case. Sometimes there are differences here, but for this case, they are equal. So in this case, we call them self-adjoint. Okay. By the way, if also those terms are 0, for instance, so meaning this term equals to this one, so in that case, we also say that the operator is Hermitian. Okay. But be careful with this definition. When you try to apply this in quantum mechanics, for instance, if you work with matrices, it is enough to transpose and conjugate. And if the operator is the same that the original one, so you say this is a Hermitian operator. But when working with continuous functions, you have to take care of. I mean, there is a little bit. It's a bit subtle to define a self-adjoint operator and an Hermitian operator. Okay, so this is the way to proceed. Typically, use the differential operator. Use your definition for the inner product and prove whether or not L dagger equals to L. But also, I mean, if you may, someone else ask you about what about the boundary terms, if additionally they are 0, then it means the operator L is Hermitian. So the additional thing to proceed, I mean, for obtaining a kind of normalization conditions for the functions un. So this is the typical way to proceed. So take your equation here and multiply this by um. You change an index dagger here and here, which is essentially this equation. So you see here, we took the second order differential equation for and then plug a dagger, star, and star. But then take again this equation, but then you put and star here, star and omega m here. Okay, you change the sign and you start the functions and then multiply by and so that you have this equation. Here it's quite easy to follow because what I mean, all the instructions are here. So then take b minus a and integrate over this range 0L. Okay, and so it's quite easy to obtain these equations. So left part, you see, this is interesting because here you see the difference between omega n square, omega m square. But here we see essentially this is our definition for the inner product of these functions. On the right hand side, you may have something related with second derivatives of u star and u and u. And the trick here, so pick this part, for instance, pick the first integral here, and then you integrate by parts. Integrate by parts, and then you will obtain this quantity. And do the same for this part. So integrate by parts again, and obtain these equations we have here. Of course, I mean, of course, you should sit and compute those two relations, but they are quite easy to follow, okay? So that when you compose, so you take this one minus this one, you see that this integral is the same as this integral. So those two integrals, they cancel out, but you are left with these two terms. So this one and this one. The way to proceed here, from here, is, I mean, this left hand side is same. So this is you leave the left hand side untouched, but then you start evaluating this. So you see this term is evaluated between L and 0. So here and here, the same here, boom, boom. But then here, what we recognize is that you may use the boundary conditions 3 and 4 that we obtained. So we go back to equation 3 and 4. So essentially, we should use these equations. So we have an equation for the first derivative of un at z equal to 0 and at z equal to L, so that we replace this and this back into these equations here. So here and here, you have to take care. The only thing that you need to take care of is on the index here. Okay, and that's it. So let me kind of summarize here. Okay, so I mean, again, just do the computations, and what you should be able to obtain is the following. So obtain these conditions. You may even you may, for instance, these terms, they appear here, because you see that you may simplify this difference, this one with this and this, and then you are left with this equation, essentially. What we want really obtains is this equation. So whenever n equals different from m, we obtain this equation. And but also we impose the normalization condition. So you see somehow, this is the capacitance per unit length, and this is the integral. So this is the inner product. Somehow this is related with the total, I mean the capacitance at the bulk, and then we have something related with the capacitance on the right hand side and at the left hand side of the transmission line. So CR, CL. And then we impose this. This is something that we impose. So we say that if n equals to m, this is 1, and the whole evaluation here will be the total. This is the total capacitance of the transmission line, which is essentially, this is C, capacitance per unit length. This is L, this is the length of the capacitance. So that this is a capacitance of the resonator capacitance, and this is the coupling capacitances, CR, CL. And well, essentially, all these equations, so equations 5, this one, equations 4, equation 4, 3, 2, and 1, they form a Sturm-Liouville problem, which is a problem for a self-adjoint differential operator. And the next part that we will discuss in the next lecture will be, well, what are the possible values? So what are the allowed frequencies in our system? And then this will be easy to follow as well, because then here we will take a genetic function here, which is already a solution of equation 1. And then we will plug this this solution, for instance, into equation 3 and equation 4, so that we will obtain the next one. The next lecture will be obtaining a transcendental equation for all allowed frequencies in our system, essentially. Okay, so but this part we will discuss in the next lecture. Okay, so whenever you have any comments or questions, please write me an email, and then we can discuss. But essentially, this is a work that you have to do with care, and just sit and compute. You should be able to reproduce all equations here. Whenever you have the if you have any comments about the lecture notes, or there are some typos sometimes, so please let me know. By the way, I forgot to mention that I miss a minus sign here. So this minus sign is missing in the previous lectures that I sent you. So I'll provide the new lecture notes with this correct sign here, minus sign. Okay. So thanks a lot.